So far we've built the oscillator, video basics, borders, ball counters, ball motion controls, and bricks on sheet 1, the paddle logic on sheet 2, and the flip screen circuit on sheet 4. We've been doing a lot of manual poking to get stuff to work. So to start tying everything together, today we're building the game state control logic, which will break up into 4 separate sections. On sheet 3 we have the start game controls and this discrete operational latch circuit. And on sheet 1 we have the ball and play counter and serve switch logic. As usual, we'll be using the RevFX schematics because the RevF schematics in the manual don't exactly match the RevF boards. See part 2 or the differences document in GitHub for details. Also note that I took the liberty to rearrange some layouts to make the flows cleaner. Naturally, the originals were hand-drawn, and you just add circuitry where you have room. Today we can easily use image editing tools to move stuff around. Just don't tell anyone I used MS Paint to modify these schematics, that would be really embarrassing. To play a game, you drop coins to add credits, start a 1 or 2 player game, then press the serve button. We're doing the coin stuff in a different video, so we'll begin with the start button circuits. We'll need a new dual D-type flip-flop in Easy 8, a new quad NAND gate in Easy 7, and a new hex inverter in Mary 9. We'll also be using an array of gates from existing chips. We'll need these 2 pull-ups, and we're using the start game buttons from our control board. If any of these lines are high, they force reset the associated start game latch, so you can only start a game while in attract mode and you have enough credits to press that button. Credit availability comes from the credit counter, which we haven't built yet, so we'll just tie these down for now and pretend. Yeah, we're supposed to have less jumpered stuff, but we're trading just these 2 for a bunch of other crap today. Button press state is checked about 125 times per second on the rise of 64 Victor 1, assuming the game is in attract mode and there are enough credits. Pressing the start 1 player game button drops the 1 credit start line and sets this latch, and pressing the start 2 player game button drops the 2 credit start line and resets the latch. Pressing either button asserts the start game signals. The start game 1 net is poorly named because it kind of gives the connotation of a 1-player game, but these 2 are simply inverted copies of start game. Perhaps A and B would have been better. Anyway, start game is presented to data in of this flip latch, which is clocked by 32 Victor when in attract mode. This brings the machine out of attract mode, which force resets the switch latches and deasserts all of the start signals. The start signals therefore end up being about 2 milliseconds wide. At this point, the machine is waiting for the player to press serve. These 2 lines go over to decrement the credit counter, and this SR latch on the 2-player side holds off force resetting the start 2-player latch while the credit counter is being decremented twice. We'll take a look at these and general credit accounting in a later video. To transition back into attract mode, we need to reset this latch. This happens at the end of a game or when this cue signal drops. I'll temporarily add a push button to this line to test. Let's turn this on and try it out. I put a few LEDs on this sideboard for some of the interesting signals we're working on today, and hook the attract line to this LED. Clear the latch, and attract mode comes on. Press the start 1 player game button, and attract mode goes off. Try that again with the 2 player button. Same behavior. Let's remove the credits. Now, neither switch takes it out of attract mode. Enable just 1 credit. The start 2-player game button does nothing, but the Start One Player button properly takes it out of track mode. Looks like everything's working properly. Super exciting. This Q signal comes from the operational latch, so let's go there next. We'll need a bunch of passives, these 4 switching diodes, and these 3 transistors which are no longer manufactured. Robust replacements are the 2N4401 and 2N4403, which have pretty much the same specs. They can handle a pinch more current, but power is really not a factor here. The latch consumes virtually no current when off and about 25 mils when on. The replacement transistors also come in nice standard TO92 packages, while the originals are in this strange TO105 package. This discrete latch controls the basic operating state of the system. When set, it allows the system to run. When reset, it forces attract mode and clears the credit counter. You see vestiges of this latch in the original Pong game in '72, and in many games afterwards. They started calling the output Q in Pong doubles and Gotcha in '73. Not sure why Q, I think it's simply named after the Q and inverted Q outputs of a standard latch, and it just stayed named that way. To me, a better name would be perhaps Run. Let us know if you have a good name for this. Inverted Q is not used anywhere else, and we can at least think of these 2 points as set and clear. At power on, the latch naturally enters the reset state because there's no active current path and both transistors remain off. At this point, our set line is high and the Q output is low. And as we said earlier, a low Q forces attract mode and clears the credit counter. The only way to set the latch and allow the system to run is to drop a coin. This turns on Q1 by pulling down its base, which then turns on Q3 by pulling up its base, which also holds down the Q1 base. This continual feedback loop is why they call it a latch. When set, Q goes high, which allows the accumulation of credits and enables game start controls. We saw how the latch is reset at power on, but it can also be reset in 2 other ways. Another way it gets reset is when a game ends and there are no remaining credits. This drops the cathode of CR7, interrupting the feedback loop and turns off both transistors. The last way to reset the latch is when a static discharge is detected by a short wire connected to pin 17. This turns on Q2, dropping the base of Q3, turning it off. This logic prevents abnormal operation after a natural static discharge and keeps unscrupulous players from trying to shock up credits. We can simulate a discharge with a light pull-up on the base of Q2, and we included this exact setup on our control board for purposeful resets. Let's try this out. I hooked the Q output to this side LED, and we'll have to poke the coin inputs manually. I'll also tie these 2 down and power it up. The latch initialized in the reset state as expected. Drop one of the coin signals, the latch is set. Remove all the credits and tie up EGL. Latch gets reset. Turn that on again and poke the antenna. Latch gets reset. Looks like that's working. This end of game signal comes from the ball and play counter, so let's go there next. We'll need a new binary counter in Baker 4 and a new quad AND gate in Able 4. We'll also use a full gates from chips we already installed. We'll need this capacitor and we'll use a jumper for the onboard configuration switch. I call Baker 4 the ball and play counter, but it also keeps track of which player is up. When output A is low, player 1 is up, and when the output is high, player 2 is up. The next outputs track the ball in play. Counter outputs B, C, and D drive the A, B, and C ball in play value. These signals are sent to the display logic, which we haven't built yet, so I'll just drop these into a hex display for now. Note that the value displayed here will be 0 through 2, or 0 through 4, and the on-screen display logic will convert this to show 1 through 3 or 1 through 5. The counter is reset when you start a game and counts up until the ball in play reaches either 3 or 5, depending on switch S4. This brings up the end of game line and places the machine into attract mode. Switches aren't really necessary for onboard configuration since they rarely change, so we'll be using jumpers on the retro board. Here we'll add an extra ground post for testing. Grounding this line will give you balls forever, which I'm sure is going to be the name of a future Bond movie. Clocking the counter is a little more interesting. You can see that this latch gets set when the game moves to the serve wait state, which steps the counter, and the latch is reset by H-Sync. You want the counter to step on the rise of serve wait after missing a ball, but you don't want the counter to step when serve wait initially rises after starting a game. The saving grace here is that the start game 1 signal stays low until after serve wait initially rises, keeping the counter reset at game start. For a 2-player game, if player 1 was up, the counter advances to player 2, and if player 2 is up, the counter steps to the next ball for player 1. For a single-player game, the counter takes 2 steps, the original latch step and a second step when output A turns on, gating 1 Henry. This moves the counter past player 2 and advances the ball in play. Since we now have our player 2 signal, we can go back over to sheet 2 and wire this into Henry 7 to generate the real player 2 conditional line. We'll use a jumper for the S2 model select switch and set it to normal for now. I hooked this LED to the player 2 line, and I also hooked this hex display to the ball number outputs. This will show the raw ball in play value starting at 0. I also temporarily added a push button to this serve wait signal and configured S2 to end after the 3rd ball. I'll reset, then start a 2-player game, poke serve wait, transitions to player 2, poke again, back to player 1 and the next ball. A few more pokes with proper transitions, and finally EGL asserts, denoting the end of a game. Reset that again. Start a 1-player game, poke serve wait, transitions past player 2 and increments the ball and play counter. A few more pokes and end of game. Looks like that's all working properly. Serve wait comes from the serve button logic, so let's hit the final section for today. We'll need a new 7474 in Able 3, a new 7408 in Charlie 1, and a new 7402 in Baker 3. We'll be using existing gates from chips we added before. We'll need a few passives, and we're using the serve button from our control board. Here we finally find that elusive 7408 in Charlie 1. This chip was added to the boards in an engineering change between Revs C and D, but you won't find any gates from Charlie 1 in the Rev F schematics in the manual. They evidently needed another gate here, not realizing they had some spares laying around from previous changes, because the schematics were not kept up to date. This is the only gate used in Charlie 1. They may have been able to make this gate out of diodes like they did for the borders, but decided to just chuck in another IC, bringing the total chip count to 103. We mentioned earlier that the raw ball signal flows through this section on its way to other logic in the video bus. The ball is always visible except when waiting to serve. This latch and gate controls the ball's visibility. When set, the ball is hidden and one or more serve wait LEDs turn on, depending on the model. The only way to set the latch and hide the ball is via the set pin. This happens when you start a game or miss the paddle. Paddle misses are detected by simply checking if the ball runs into H-Sync. The only way to turn off the latch and show the ball is by clocking in low data. Data in is checked once per line at the rise of the clock when 64 Henry and 32 Henry go low, and 128 Henry and 16 Henry go high. That combination of signals lands here, but we're only looking for entry to that state which happens along this line. For data in to be low, either of these inputs must be high. When set, the inverted output feedback line is off, so the other input must go high to reset the latch and show the ball. Following this line back, both of these lines must be low, so this latch must be on and the ball must be present when this clock rises to turn off this latch and start showing the ball. That means that the ball is hidden until it crosses this line, ensuring play does not suddenly start in the near field area. This latch is reset when waiting to serve, fencing off the ball signal. The latch is set by either entering attract mode or by pressing the serve button. When set, the ball signal is allowed through to possibly reset the serve wait latch when the ball enters the near field area. You can see here how the SBD signal is generated when you press serve, and we can now bring this over to our X motion control to force the ball to move towards the player on serve. Before we fire this up, I want to create a thin line where the ball should appear. We'll gate this clock using additional horizontal signals to narrow it down, keep it out at VSync, and drop it on the video bus. I'm also going to drop a weak copy of the ball signal so we can see it even when hidden. This should give us a better idea of what's going on. I also hooked the serve wait signal to this LED, power it up, initializes into attract mode. I'll then press the start one player game button to bring up serve wait and hide the real ball. You can still see our weak ball is bouncing around, and the real ball appears when it crosses our clock line. Allow the ball to miss the paddle, and the circuit transitions back to serve wait, and increments the ball and play counter. We're finally at the point where we can play an entire game cycle with the proper controls and behavior. We've pretty much tested everything except flip screen. On an upright model, player 2 uses the same controls and the screen stays put. On a cocktail table model, the screen is rotated when player 2 is up. Let's jumper the model switch for a cocktail table and quickly check out today's work. Screen flips when player 2 is up, and the ball appears properly in the near field after a serve. We don't need any new parts, so let's just throw today's stuff into our schematics, starting with sheet 3. Rename everything. And wire it up. Move back to sheet 1 and add gates. Rename everything. And wire it up. Well, we're getting there. Nothing new visually today, but we had to get the game state controls done. In the next video, we'll work on scoring and the on-screen display. Thanks for watching.